be here. It's particularly a pleasure for me to be at YITU, and sorry for my pronunciation. And it's a great pleasure to me to see how well YITU is doing. So my talk is on deep networks and beyond vision and machine learning, and the green one is for that. Okay. And I guess what I'm interested in particularly is what can AI do and what are its limitations. And I almost called this talk "When Big Data is Not Enough," which is part of my theme. So the current successes of AI is discussed due to three factors: deep networks, reinforcement learning, machine learning methods, the vulnerability of large annotated data sets, powerful computers, and GPUs. But I think there remain very important challenges. There's a long way to general-purpose AI systems with human-like abilities, and I think we are quite a long way away from that. And I think some of my views would echo Christoph and certainly what Jeff Hinton was saying, quoted there. I'm going to talk about vision because that's my area of expertise, but I think similar issues arise for other areas of AI. So what deep networks can do, they're a very powerful processing tool, and they can do things like face detection, recognition, text detection, recognition, medical image analysis, and many, many others, though I'd still say up to a point. Example of things that they can do, and this is a project we do, the Felix project, which is CT images. And here what we have is a nice combination. We have expert radiologists. They do really good quality annotation. We throw machine learning methods at it. We get pretty good results. This is actually from last year. I should update it with what we can get this year, where we can get sort of cancer tumors out at fairly similar levels of accuracy, and performance is very good. But this, in a way, despite being a challenging data set, is actually quite an easy one, because it's not going to have the same issues that are, I think, going to arise in more complex situations like the ones we've got here. So deep networks basically work when you've got enough data, annotated data and training, and you can, of course, also use them when you've got less data. So you do have transfer learning. You can build a system for recognizing whether people are in pain or their degrees of pain, even if you don't have a lot of data for that, because you know that the facial features that are going to matter for finding pain are going to be similar to those which are used for doing face recognition. So you take it, for which there's lots of data. So you take a system that's trained on face recognition, face verification, and you only need a little bit more data to transfer that and to learn pain. Similarly, you can do few-shot learning, where you can use pre-trained features on certain data sets, and then only a few examples of new ones, of new objects, in this case, are needed in order to recognize them. But there is a careful caveat here. What you need to, in order to get that to work, or at least our system, which is one of the state-of-the-art at CPR a month or so ago, is you need to be trained on a fairly large representative set of objects, and then you could transfer and you could do few-shot learning on others that are somehow similar. This is arguably a little bit like a child learns. A child learns very slowly up to a certain point, and then they speed up enormously. And one way of thinking about that is that maybe they're building up a vocabulary over time, which takes them a certain amount of it. Once it's big enough, then everything becomes easy. So success of the deep networks in these cases, transfer learning or few-shot learning, occur after it's already built up the right sort of dictionary, and then you can get away with this type of procedure. Now, deep networks, of course, is not just sort of like a static thing. They're still improving. There's been a whole history of them developing, for AlexNet, VTG, ResNets, etc. there's been automatic search for neural architectures, there's been a whole lot of things, so it's no longer static, and it's really quite an active area. But, okay, what are the limits? And so I'm going to bring up some things which I think are potentially serious limits to how we, we work in computer vision at the moment, and where I think probably new ideas are going to be needed. So one, there are limits to the functions that deep networks can learn and represent. Now in principle, and I know there are theorems which prove that a deep network can represent almost any input-output function, and in the past I have either proved or co-proved things a bit like that. So I know those theorems exist. I also know those theorems are not very helpful, because they don't give you bounds or anything about what you can do with a particular network or anything of that sort. Two, there are limits, weaknesses of deep networks to adversarial examples and other types of attacks. And third, I think there are limits to annotated data sets and to big data. So, what can deep networks represent? And I know I get in trouble with this with some audiences, but I'm saying that I think deep networks are almost really memorization devices. Very, very smart memorization devices. They can store and they can interpolate between examples, but I don't think they can really abstract or extrapolate to unseen data. Humans can do this. Adult humans can recognize a blue tree even if they've never seen a blue tree in their life, as few adults have. And we have that ability to transfer, abstract out in some sort of way. I'd also say deep networks are really very sophisticated regression methods. Regression goes back to Gauss in 803, and I think if you showed a deep network to Gauss, you'd probably understand it in about half an hour and appreciate what it could do, but perhaps also appreciate its limitations. Now, I said I think what deep networks can represent is limited, and it's not always clear what they can or what they can't do, but I would say that they're suitable for tasks that can be done by storing enough templates, which is a bit like saying by memorization. And, as I tell some of my students who have greater belief than me in the powers of deep networks, you shouldn't really ask a deep network to do too much. There are some things which they're good at, some things which they're not, and, you can't pin it down quite mathematically, but you can pin it down generally after a certain amount of experience with students who go ahead anyway, and several months later they agree you might have been right in that case. Okay, so limits to what they can represent. They can learn to remember patterns. They certainly have no ability to understand the causal rules that generate these patterns. And so analogy, as an ex-physicist, think of astronomy. The solar system could be described pretty accurately by Ptolemy's epicycles. Okay, that just sort of, it described pretty well what was going on. It represented the data, but it didn't give any understanding of why those laws, why that sort of pattern happened, and it required Newton to do that. The epicycles were very good. Even after they had Newton's laws, I was told that people still used epicycles because they were really pretty accurate for our solar system. But Newton's laws could tell you what was going on in some other solar system that you'd never been to, and Newton's laws could tell you what would happen in our solar system if there was a rogue planet or something that came in and changed everything. So there's a difference between causal understanding of things and memorizing patterns. So for vision, what would be a causal model, and a very simple, trivial example is think of computer graphics. A computer graphics model will render images based on 3D structure of the surface, texture patterns, lighting, and stuff like that. Okay, deep networks can be attacked. Tiny imperceptible changes to images can defeat deep networks. you add a little bit of an image onto a little bit of noise onto those pictures of two trains, and you turn it into, I've forgotten what class of object they think it is, airplane, and you'll agree the shape of the airplane is rather different than the shape of the trains. And similarly here, you take an image that's perfectly blank, add a bit of noise onto it, it now becomes a bus, it has that type of shape as well. So, of course, this is one type of attack at the deep network, and there are certainly defenses against these sorts of attacks, and there's a bit of an arms race between them. But even so, at the moment, the fact that you can attack these is slightly problematic. And I'm not seriously thinking that people actually attacking your algorithm, an enemy trying to do it. It's just the point that there are some images so similar to the ones that you're classifying correctly, which your network is now not classifying at all, is deeply worrying. Now, in this particular example, I have reasonable hopes that these types of problems can be fixed in the, within a few years. There's some interesting ways of defending which are quite, which are, I think, smart and have nice theoretical bases. So these things may go away. I'm more worried about the types of attacks that come in here. So here we have a monkey, and the monkey is then given a few objects, and now, just because it's given a few objects, the monkey gets turned into a human, presumably because the algorithm has never seen a monkey with a motorbike, a bicycle, or a guitar, and so it has seen a human with those things, so it starts thinking that the monkey is a human. Similarly, over here, the objects, however, get reinterpreted, so the guitar makes the deep network think the monkey is a human, but again, the deep network has never seen a guitar next to a monkey in the jungle, and so it starts thinking that the guitar is a bird, and the handlebars of the bicycle are now seen as being a bird as well. And so the first type of attacks, which are just local types of noise added to the image, don't worry me too much. I suspect there will be solutions to this. But here you're talking of occluding the object or changing the background. And my concern leading up to one of my main points is that you can do that. You can occlude objects in an exponential number of ways. You can change backgrounds in an exponential number of ways. You're moving up to a level of complexity which is really hard to deal with. So limits to annotated data. Yeah, there's lots of good results about deep networks applied to particular tasks, and here is here is the sort of the other side. Annotated data sets bias the research community to working on vision problems for which there are high-profile annotated data sets. Now, there are certain things for which annotation is fairly easy. Putting a box around objects is quite easy, and Fei was very smart to do that. And that means that performance on knowing whether there was something in a box is actually quite good, though I would dispute the fact that it's a human level performance, but it's still not bad. But it's hard for doing other types of tasks, such as estimating 3D and estimating parts and things like that. So that means that the vision field in general is sort of not working a lot on those sorts of problems and only working on those for which annotation is straightforward. Point number 2 is that the image data sets are only partly representative of the complexity of natural images. Rare but important events may not occur in the data sets. And I heard this from a talk by people in NVIDIA. You want to have automated cars, you get lots of images of roads. How many images have a baby lying in front of the road? The answer is not many, and yet that is precisely the type of situation you care about and you ought to care about. So rare events may not occur in the data sets, and your system may not care about them, its worst case hierarchy. Point number 3, it's impossible to follow the principles of experimental design and vary the factors in an experiment systematically, which is sound sort of scientific practice in general. But you can't really do that in a data set of images. How can you? It's almost impossible to imagine how you can do it. But after all, if you want to have an algorithm that says it can detect a chair, to know that it really can do that, we ought to be able to vary factors like the viewpoint, the lighting, the material properties, and even the shapes of the chairs. And you can't do that in annotated data sets, or at least not in any annotated data set that I've seen so far. For some vision tasks, the data sets may never be big enough for current deep networks. Here again, you have to agree with me somewhat that deep networks are essentially sophisticated recognition devices and don't have the ability to have enough causal understanding to generalize to other situations. And the issue here is that for complex vision problems, I'd argue that the amount of data needed to train and test the vision algorithms may become exponentially large as the complexity of the visual task increases. Okay, so we can deal with data sets, we can deal with enormous data sets, there's enormous amounts of data coming out, but exponential growth in size of images and so on is not something that's possible to handle. Why should that happen? It could happen because images can be constructed in a combinatorial number of ways. You can pick objects out of 20,000 objects, you can move them around, you can vary the lighting, you can include them, etc. And you have a combinatorial explosion sooner or later. And if you buy into this, if you believe my argument so far, then you have data sets which, to be representative of the complexity of the environment, need to be exponentially big. And how are you going to train and how are you going to test algorithms under those situations? Now, I'm obviously not saying we should give up. I mean, I'm actually reasonably optimistic in the ways of solving this. All I'm saying is that current approaches of just throwing deep networks at it is not going to be the method to do it. We've got to have something else. So, another way to think of the numbers of data sets is here is a data set Pascal that was a big data set before ImageNet, and here is a synthetic data set that was rendered from ShapeNet by people at Stanford. You're going up from 10K to 2.4 million images. By ShapeNet, you have models, three-dimensional models of objects, and you can control the camera pros and so on like that, and you can get a data set that size. Okay, so now, and so if you buy into the idea of synthesizing using computer graphics, you can imagine generating enormous numbers of images, you know, again, exponential numbers. This was created by one of my students. I like the idea because the idea here is that the set of images in that are visible are above the water, the ones that are invisible below the water. So I like the concept, but I said I don't like it because for icebergs, 90% of the ice is underwater, but I think for images, it's not 90% that's under the water, it's 99.99999 up to some enormous number that's under the water that you can't get. Okay. So here, again, thought experiment, images from synthetic computer graphics model, camera pose 4 parameters, lighting 4 parameters, texture 1, material 1, scene layout, 13 parameters, 10 cents to the third values of each, and put that together, you get 10 to the 39 just from that really simple situation. Okay, now that may not matter a lot because for a single object, maybe, you know, of those 10 to the 39, it really lies in some lower dimensional space approximately, and memorization devices may still work, but it should at least start making you think. And that's just for a single object in the scene structure. Now you allow occlusion and multiple objects. And you can occlude an object by putting any other object in front of it. And This alone could be exponentially complex because the number of objects you could pick, 20,000 of them, and then you could pick them in I don't know how many positions, and you've got an exponential number of things as well. Okay, now you can get around this partially by saying that certain deep networks don't care very much about occlusion, but I think that's being a little bit too optimistic. They're able to deal with certain amounts of occlusion, but not nearly the amounts of occlusion you can start putting in. And then it gets even worse if you start thinking by constructing a scene like this, where you have so many different objects, so many different positions, so many different configurations. You really are, as far as I can see, in this combinatorial situation where the data sets are huge. So text captioning was brought up earlier, and even though we've worked on this, and thanks to having a really brilliant student, Jun Hua Mao, we were getting state-of-the-art methods on this. Time it was published, but this is an example where I think if the images are large enough and the captions are rich enough, you're going to run into this exponential situation. You know, if you just have a caption of a small object, that just takes one or two objects in it, then I could believe it. But if you start allowing this to be anything, any possible configuration, it's not going to work. And so there are text captioning systems that you can download from Facebook and places like that that have been trained on enormous sets, and the results are often quite good, and every so often they're incredibly bad. So I think in this case, we're moving into situations where the amount of data to be representative of the real world, if we're using current techniques, just is so big, you won't be able to train, and even more, you won't be able to test. Getting back to experimental design issues, this is something we did. Student WAIC was doing this. You take an object detector trained on ImageNet to find sofas. So, okay, you make a sofa, and then you sort of can vary the viewpoint, you can vary some material properties. Can the algorithm trained on ImageNet work on this? And the answer is sometimes, yes, it will work very well. Sometimes it will work really badly. Why? Because even though the ImageNet is big, it doesn't contain all different types of sofas, seen from all different types of viewpoints, with all different types of material properties. How could it? That's a very large number of sofas. Okay. So so with computer graphics, in terms of creating data sets, you could potentially create exponentially big data sets, because if you can parameterize the world, you have a machine that can generate everything. Except you could never generate all of them and store all those images on it. You can never train algorithms on it. You can never test algorithms on it at all. I mean, I'm in favor of computer graphics, despite the fact that we have a little bit of difficulty getting our papers past the reviewers. But this is because I think they're making fairly important points here. And another one here is the sensitivity of stereo algorithms to hazard factors. So if you want a stereo algorithm to work in a car, particularly if you're driving the car late at night and there's a lot of rain about, then if you know anything about stereo, you know that stereo algorithms work badly if there are specularities, because they rely on matching parts of the image from the left to the right eye, and if they're specular, that's not, the intensity or the features in one eye are not going to correspond to the features of the other eye, because specularity, the images of specular surfaces will change from one viewpoint to another. Okay, so shouldn't you try to test stereo algorithms under these conditions? Well, you can go to the very big data sets, like Kitty or something like that, and you find there are a few examples like that, but there aren't very many. And also, it's a pain to annotate them, so nobody's really bothered. But using computer graphics, you can test this out. You can sort of systematically explore the space of specularity and other hazardous factors that can make computer vision stereo methods fail, and you can see which ones are robust to those and which ones are not. Because after all, if you want to move computer vision to the real world, you need to know what the worst cases are of your algorithm. So it's encouraging that YITU's face recognition system has got, whatever, 1 over a billion or whatever number was quoted earlier. We'd like to have that for everything. You don't really want to know what the average result is going to be. You would like to know what the worst case result is going to be, particularly if you're detecting a tumour in a CT image, or if you're trying to drive down the road and make sure you're not going to run over a baby or some homeless woman on a bicycle, as happened with Uber earlier in this year. So the case I've been trying to make is that if you throw deep networks naively at certain types of problems, you'll reach situations where the amount of data you have is not enough. And I would claim that applies to a number of vision problems that people have been working on in the last few years. I don't think that really applies so much to faces, because faces are fairly well constrained, and so it would work well on those. I think it doesn't apply that much to CT images, because in CT images you don't have these issues like occlusion or lighting variations or any of the things that make the real world more complex. But I think it will apply to other things. I think it will apply to text captioning, it will apply to various types of action recognition and so on. And I think the field may be simply overfitting the data sets, and results will not work when you go outside that type of, outside of that condition. So I think we need algorithms that can generalize or extrapolate away from the training examples, and so I have a long time been in favor of compositional models because they seem to have an ability to deal with a scaling thing. So I go back to Leo's PhD thesis, where I had some nice work on compositional models. I think some of the points that Christoph was making about, connections between neurons means that you could potentially store an exponential number of patterns in that way, if I understand it, and I think that's potentially a value. Whereas if you take the idea that deep networks are basically just doing templates in a very sophisticated way, I don't think you've got any way of dealing with with this exponential situation. So I think we need new algorithms that can generalize. We need to be able to learn from limited size data sets. I think the learn like a child idea could be correct. You learn enough of the vocabulary. It can take a child 3 years, rather slowly, to get to that stage. Once it's got the vocabulary, once it's got the dictionary, the child can then learn quite easily after that. We must be able to test over infinite data sets. I think computer graphics enables us, it's becoming realistic enough that you could use computer graphics to at least explore how an algorithm is working over a huge data set, although you still have to sort of check it out on certain real images as well to make sure you're not just working in the toy world of computer graphics. Testing over an infinite data is impractical. You can't do it. So the idea I like here is to sort of exploit the idea of attacks, exploit the idea of adversaries, so that you can have an opponent, and this becomes more like game theory than decision theory, an opponent who tries to find a stimulus that can destroy your algorithm. So let your worst enemy test your algorithm by exploring through this sort of exponential space of configurations to find the one that can hurt your algorithm the most. So I'm arguing that the fact that current methods don't seem to have the abilities of that, well, my thesis is basically the data sets to be representative in certain cases have to be exponentially big, and the current algorithms are not going to work well on them, either for learning or for testing, and we need to be able to deal with that if we want to move on to the next stage. I'm saying guidance from cognitive science and neuroscience. In a sense, I'd love to have guidance from cognitive science and neuroscience. I'm not sure those fields are mature enough to give us really good guidance yet. But just to take the point that the human visual system is much more flexible and general purpose than any computer vision algorithm. We can generalize to situations they cannot see. We can extrapolate much better than deep networks. We have causal understanding. We use only a tiny amount of power for that. The brain needs about 20 watts, but most of that is just keeping the brain alive, and the amount of just computation is only 1 watt. That's tiny compared to the amount of computer power used by DeepMind. In fact, you can argue that when DeepMind won at AlphaGo against the Korean champion, it was really unfair to the Korean champion because he apparently consumed 1 sandwich during the whole game, which is the amount of energy he had, whereas all the computers that DeepMind was using could use, I don't know how much power around. So humans have these types of abilities. In defense of humans, I would still say that humans can do better than deep networks, except on certain tasks such as circuit board inspection, which humans find rather boring, or tasks where they have to find the names of some obscure dog that they never actually heard of, which the computer can recognize. So I think we can learn a lot from the computer vision, learn a lot from human abilities and cognitive science in the sense that it aims to understand that. So in conclusion, I don't want to sound too negative because I think deep networks and big data are very useful, and for certain problems they're incredibly effective and they lead to lots of real useful applications. But risks that AI will take over for humans are science fiction, partly because I think to get AI to the level where it's working like a human, at human level performance, we have to deal with this sort of complexity exponential issue, which we haven't really scraped the surface of. And I'd say that doing this might require learning from understanding of cognitive science to understanding the brain to the extent we can do it. Anyway, so this is my sort of polemical talk, which I've started giving at computer vision conferences just to stir things up a bit, because so much computer vision work is driven by the rather boring idea you have a data set, you throw a deep network at it, you twiddle with the parameters of the deep network to make it do a bit better, you try and publish a paper. Now for a company that's not a bad strategy if you've got enough data, because it really matters how well you do, but I think for the computer vision community we ought to be aiming at studying more fundamental problems and issues